Russian Quantum Center, and I'm very pleased to have an opportunity to be here. And now I'm going to speak about frequency element method simulation of thermal noises in Whispering Gallery Mode cavities. So, yes, I will give another brief introduction of the Whispering Gallery Mode. So, the main idea is if you have some transparent material, you have there some total internal reflection angle, and you can make light circulating inside this cylindrical cavity around the circumference, and it will not go away in classical approach because of the total internal refraction. In wave approach, the mode can be viewed as some field that is oscillating about the circumference, and from the cross-section view it can be one dot or more dots in this direction. Well, you saw that in Hiron presentation. Well, what is important here is that for the fundamental mode, and we basically are interested in fundamental modes, we can get some parameters, for example, the radius of this mode in both directions and its position. Well, you can see the formulas here. I actually use them in simulation to simplify it. And the most important thing is that this mode can be exactly seen as the following. So the azimuthal dependence of this mode is exactly the complex exponent, with the m, the azimuthal number. And of course, they can be T or Tm, depending on the direction of the field. So now we turn to thermal noises. To calculate thermal noises, I use the fluctuation dissipation theorem. In its first formulation, it says that the source of dissipation is the source of fluctuation. And if we have some generalized coordinate that can be expressed in terms of the corresponding force with this coefficient alpha, you can say that, okay, I go to Fourier dimension, and then I have this relation, and I take the complex part of this alpha, which is corresponds to the dissipation, and we have this wonderful formula to get the exact spectral density of the noises. This theorem was a bit expanded and reformulated in so-called energy formulation. So if we are interested in some observable that can be expressed in terms of some generalized coordinate with integral relation with the form factor Q, and we want to know the fluctuations of this observable, we should do the following. We introduce the generalized force that has the same form of this form factor, and it is harmonical, and act with this force onto our system. Then we can calculate the dissipated energy. No, sorry, this is not the dissipated, it is just the definition of the relation between the generalized force and generalized coordinate. So after we apply the force, we calculate the dissipated power over one period, and again we have this beautiful formula to get the spectral density. And that's exactly the thing what I'm going to do in COMSOL, because in this formulation it is very easy to do that. So what is next? We'll discuss our observable. Our observable is apparently the frequency of the cavity. So to get insight on this observable, we have to watch we express our field as the following. It is, of course, some oscillations, and here G, that is mode number, is formed from the three of that related to the Whispering Gallery modes. It's azimuthal number, vertical number, and radial number. Then we have to understand what is the source of our fluctuations. So the simplest way is to introduce a perturbation of the permittivity. So then the Maxwell equation can be rewritten in the following form after this substitution. Where here this is the unperturbed permittivity and the small perturbation. And from this equation we can see that it is something like perturbation theory. We can see that our deviation of the frequency corresponding to this deviation of perturbation can be expressed in the following way, where these average amplitudes are not very well defined, but we can say that in stationary they are proportional to the following factors. So this is just Lorentzian on the frequency, which is just the time domain resonance, and this relation is the relation of the pumping. So this F is the form of the pumping. It can be a form of the field from the prism or waveguide or fiber, anything, and it is we calculate the overlap between it and our mode profile. Well, okay, this thing contains the frequency part. We can, if we assume that we are probing exactly at the resonance, it can be a bit simplified, and the important thing that this relation can be close to 1 for different remote MP and Q, because well, only there we have this difference in the frequencies small enough. And in particular case for the sphere, this relation is the following. So if we fix the frequency, there will be practically the same if m plus p is constant while we'll sweep through those modes. The second overlap path can be simplified from 3D integral to 2D integral if we assume that our pumping is good and the phase matching is good. And the interesting thing that this can be close to 1 only, of course, if we have the same polarization of our pumping field and our mode we're interested in, and if the P has the same evenness, so I mean it has the same symmetry over the horizontal plane, and of course it is close to 1 only if we have same P and Q, but it really doesn't depend on M. So if we combine this, we can see that basically this whole factor can be close to 1 only for the mode we are probing. All other modes will have about 10 times less coefficient. And this allows us to highly simplify our calculation for some cases. So we don't need to calculate all the modes. And now we come to a thermal refractive noise. It comes from the change of refractive index while the temperature is fluctuating. So from the observable The observable transforms to this one. I just take that expression I have before and input here the deviation of permittivity. It is straightforward that our generalized coordinate will be temperature deviation, and generalized force is entropy density, because if you multiply them, you get the energy. And our master equation is the heat transfer equation in the following form. So we have this heat transfer part and our pumping that comes from the estimation of Whispering Gallery Mode profile. It is quite similar to what Amir did on some days ago when he calculated the heating of the Whispering Gallery mode. And the last and very important thing is the dissipation energy. Well, there is some formula that allows you to calculate this thermal dissipation. And that's the theory, and I think that now we can go to the modeling. So, any questions? Yep. Yes, it's natural, it's fundamental.
Why do you have intensity in your equation? Why is intensity basically somewhere, like you can, that E squared is this intensity, if I'm not mistaken?
Yes, it is intensity, but I don't really care about how I call it. So
Why the amount of basically thermorefractive noise you get from just
you can get to this from the different ways. So if you have some fluctuations of your refractive index, well, I don't know. For me, it is straightforward that the amount of the fluctuation that is transduced to the frequency is proportional to intensity, because, well, it's just a weighing factor that is probing your noise. For example, when we studied the LIGO mirrors, there we used the Gaussian profile to input in this place, because you probe your mirror with a Gaussian wave. And then there we had the Gaussian here. And here you can think that you probe your fluctuations with the Whispering Gallery mode. And that's why you have intensity here.
Basically, a mode volume.
the frequency is 2 pi r times n, and beta basically nu is just 2 pi r beta n, right?
Yeah, I think what Amir is asking is, it looks like in your master equation for heat transfer, right? It looks like you have something that's weighted here with the normalized mode profile.
Mm-hmm.
Yeah, so there's nothing, these are just normalized units, so there's no principle, you should not carry any intensity. So I think Amir's question is,
yes, maybe, because of course those mode profiles are normalized to energy. They are normalized to energy, of course.
but still, why do you actually, why they appear in your master equation instead? Why they appear in your master equation?
Well, it appears according to the method. As I said,
You don't solve for a source as a delta function, but the source here.
It's a kind of mode volume, I think.
The source is the heating, why did it right? Absorption of the laser.
no, absorption is not here.
These are normalized.
It is normalized form of the mode, which gives you the weighing function with which you are probing your noise.
It's a geometrical factor.
Geometrical factor, yeah.
So what you're doing is, instead of solving this equation for, say, delta function, which is the Green's function, you solve directly on the proper eigenfunction of the optical mode.
Mm-hmm. So, yes, now we can try to go to the simulation. Where is my COMSOL? Here it is. So not that. You can find and download it from the site. Where is it? Thor sphere. Yes, here it is. I already made the geometry of the sphere because not to waste some time. And here are the parameters. I have a sphere. It stays on leg. And as I said, I will use some other calculation, other initializations. I put them into the file, which is called WGM param. You also can find it in the Google Drive. And it is I input it here to the parameters. And it has all the formulas for the dimensions of the Whispering Gallery mode and some other constants that are not included in materials, for example. So I have this radius, I have to input it here. And as I have the sphere, I input it also here because these calculations are made for the torus. And if you have a sphere, then you just have both radius of the torus equal to this radius. And here I get the thermorefraction index and elastorefraction. I will not need it right now. I also have the temperature and pressure. I also don't need it. Here is the wavelength. And after that, we can calculate those FSR of the cavity, its dimensions, and the initial guess for the M number. Then, well, here actually we have the list of things that we should do. Now, why I need all those things? Because the sphere is quite big and the dimensions of the mode are quite small. So to see it by the eyes, I just add another ellipse. I name it WGM. You just press the button. And here I write DRE. It is the dimension of the mode in radius for TE mode. Here I say DZE and 0E. And I plot it, so there is my mode. There is the estimation of my mode. It's very small, so I don't want to calculate and mesh the whole domain. So I have to make another domain. I put here 17 DRE and here 17 DZE. And forgot. And here I have R0E. And I make it the center, and that's the region I'm going to model. And I name it VGM region, and there is that thing. It is the tick box resulting object grade selection. It is a quite useful thing because, and I usually do this thing for every geometry object I make, so it will be more easy for me to assign materials and physics. So then I add the material. It will be air everywhere, and also silica glass for my sphere. So there's the selections, and I search for the VGR, and I instantly get all the regions I have to fill with silica. And you can see that I didn't remove the selection for the air because it is automatically overridden with the material that is after it. Then I add the geometry. It is 2D axial geometry, and oh, sorry, mixed up things. I am adding the physics, just like the previous speakers did. I add the physics, and it is going to act only at my Whispering Gallery mode region. Then I input here the estimation of the mode number. Here it is, the azimuthal mode number. And then I initialize the study. It will be an eigenfrequency study. And the central frequency will be the frequency of interest. As I remember, it's 630 nanometers. It was also calculated in parameters, and then I just press compute to just look if everything is all right. And I also consult my list of things I will have to do. Yes, I'm now at this point. Oh, at this point it is initial calculation, so it shouldn't take much time, about less than 30 seconds, yeah. And here is my mode. It is exactly as I expected in the region. Well, the introduction of this region also helps me to do the finer mesh, because the mesh automatically finds that here between this imaginary circle and the circumference you have a small gap, so it automatically increases mesh there. So basically this is usually sufficient, and I don't have to refine it. So the only thing I'm not happy with is that the frequency is not really the one. Oh, sorry, the one I need. I can check it. And to slightly shift my initial guess, I also have some predefined things there. So I expect that the frequency spectral range doesn't change very much, so I can invent this correction for the azimuthal number through this FSI, and I just need to input here this frequency. It is 4.82, well, doesn't matter, E14. And so I see that I should correct my azimuthal number by the 13. And here at the end I have this M current azimuthal number, which is ME plus DM plus MS. MS is the signal mode number that I will sweep afterwards. So I input M current here instead of ME. M current. And now I want to sweep because I want to check the noise for all those modes, and to calculate that factor of amplitude relation that I was talking before. So I add parametric sweep for M S. And I'm going to sweep it from -3 with a step of 1 to 1. Why I do it from -3? Because of that I want to see that relation I saw before, that the frequency are going to be very close for m plus p constant. And well, that will be the graph I will want to see. This simulation also will not take a lot of time, about a minute. And then, well, I'll take this time to maybe speak about how I am going to feed those results from electromagnetic wave to the heat transfer. To do that, sorry, I will introduce the more variables with the file called Whispering Gallery Mode Variables, EWFD cross. That's the text file, which is table-like, and I will input it into variables section. And the function I'm going to speak now is the withSol function. This function allows me to take the results of a given solution. This time it will be conjugate of electric field for particular mode numbers. So I input the current signal number to the signal number, and I take the number of solution, the number of the wave frequency that is made with this PQS variable. And and here there is how I calculate that pump function. Okay, so now I've got my solution, and for ms equals to 0, because it is the deviation of the central, I have the frequency much more close to the one I expect for the 630 nanometer wavelength. Oh, I forgot the main step, yes. I have to input here those variables. So under the definitions, I introduce the node variables and import the file with my variables. So here it is. And as I already made the calculation, but I didn't have those variables with me, I don't really have to recalculate, but I still have to push this magic update solution button. It will take much less time than recalculation. So now I have my form factor with me, and I'm going to initialize the heat transfer model. Okay, so I go to add physics and add the heat transfer model. The problem with heat transfer model is that by raw it can't calculate things in frequency domain. Oh, by the way, I can see that I didn't apply the silica to the leg of my microsphere, but it was irrelevant for the Whispering Gallery mode calculation because it was only in this small domain. But the heat transfer will be at the whole cavity, so I tick here Whispering Gallery Mode Resonator and the lag. What's then? I'll consult my file. So now I'm finished with this, and I go to heat transfer. So now I have to add the azimuthal dependence, because if you look at the equation, this guy, well, not this exactly, but if I want to check the whole thing, this guy is dependent on the mode number, azimuthal mode number. And if I introduce it to my heat transfer equation, the solution for the temperature will also be dependent on the azimuthal number. So I have to add this thing. I add the wick contribution with the following thing. Wick contribution is another node for the physics. There is a small probability that you do not see them because, in fact, we're doing some advanced things. So you should probably switch on the equation view, advanced physics, and advanced results thing in view menu. And then you will see this contribution under more, wick contribution. Physically, it is just some form of expression that I want to add to my equation. So for the row, the heat transfer equation is like this. If I go to the cylindric symmetry, I introduce my temperature in the form of this exponent, complex exponent, and after taking this gradient, you will have there Im over R that came from differentiation of your complex exponent over the phi dimension. And well, it is a way to introduce phi dimension to axial symmetry problem. Is it clear? Not yet.
It's something that is like embedded in the software when we specify that we want this axis symmetry.
Yes, it was embedded for electric magnetic wave frequency domain. So it was exactly what this thing do. If you dive into equation view, you will see that there in the expressions, not really here, but doesn't matter, you will find that Im over R thing. And to add this to the heat transfer in solids, I have to do it manually. So here it is, M over R and T test T. It is some syntaxes of the wick form equations, but the idea is I just add that missing thing to the equation.
So the adjective weak here has to do with the numerical weak form.
It is the numerical. No. It is the weak form. The weak form of the equations that is used in COMSOL to solve the things.
And where do we learn how to?
You can learn about it in the help section. And I did not press that. Somewhere over there you can find all the documentation of this weak form formalism. It is closely related to that minimal energy principle and variational problem statement. So you will type here something like weak and press search, and I think you will find it. And I apply this to all domains. As the parent have only those domains, then all domains means only all domains under the parent. Okay, So I made my heat transfer equation really axisymmetric, and now I have to add another weak contribution, which is related to frequency domain calculation, because by rho, heat transfer model can't calculate frequency response, only time domain response. I'll again consult my text, and I take this weak contribution for frequency domain handling. It is just time derivative of complex exponent related to time. That's all it, just literally. I have rho, Cp, and T, and this minus E 2 pi F. And that's the bit from the weak formulation. And I also apply it to all domains. Is that all? No, I have to insert my pump that I was calculating past many minutes. So I input the heat source. I apply it to the Whispering Gallery region, and it is appropriately truncated to only the place where I actually calculate. And I input here my form factor. Here it is. I just copy it. And this TR form is defined in these variables that I imported. And it should be fine. And finally, I have to input the boundary. I will use the heat flux boundary. I also push all boundaries, but COMSOL knows where to apply it. It should be only the outer boundaries, so it is just some programming sugar. And I think that this thing is in air, so I put heat transfer coefficient for air. It was 10 or 11, I don't really remember. And the other important thing that I have to, I'm solving for the variation of temperatures, so all the temperatures and its initial conditions should be 0. Yeah, something like that. I check if I miss something. Yes, beta are already made. Oh, and I also have to file the thermal vars, which contains the other part of the spectral density calculation. So it is, here it is, thermal vars/T. Here we have the prefactor, that is Boltzmann constant of T and so on, and this dissipated energy calculation. And now I have to add study. I haven't done it yet. The study will be only for heat transfer equation, and it will be stationary. It will be stationary, but I'm going to sweep the frequency, so it will be frequency domain study, some artificial one. And I add the parametric sweep over the pump mode, that's MP, and over the Fourier frequency, where it is, here it is. The pump mode, I mean, when I use those with SOL functions, they are initialized so that, I just put those mode numbers I want to calculate, and one of them was MS, which I was calculating, and it was here in parametric sweep for the electromagnetic waves. But now I'm going to sweep not signal mode, but the pumping mode. So I have another mode number, and it is also in those equations. If you want, I can show them, but I don't really feel like to. And I also sweep it from -3 step 1 to 1, and my Fourier frequency is swept from, I will sweep it in logarithmic scale, so I put here from, well, first of all, I will use number of values, not necessarily, from 0 power to 7th power, and number of values will be 10. And I apply the exponent 10 function, so my sweep is as following. I have numbers from 0 to 7, I have 9 of them, and I use 10 to the power, so the steps will be 1 Hertz, 10 Hertz, and it's just logarithmic. And then I hit the compute, and if I forget something, and he will remind me just now. Because I have parametric sweep of 2, there are 2 different ways to do it. Yes, of course. Following feature has a problem. There is this menu, and now he was trying to calculate only specified combinations, and he gave me an error because here I have only 5 sweep values, and here I have 10 sweep values. So I change it to all combinations and press compute. This one will take some more time, and I forgot another thing. I can also sweep. Now I'm sweeping for the M number. Yes, question?
Just wondering, this specified combination, is it like a zip that it goes through?
No, it's one by one. So you can input there just an array of numbers here and here, and he just gets first, second, third, and so on. Now I'm sweeping through the M number, but I also can sweep the transverse mode number with those MPQ. And if you open, or maybe not, I don't remember. No, I didn't put it here. You can do it yourself afterwards, by the way, like an exercise. I also didn't show one thing. I didn't show you the calculation of this prefactor, but it's quite straightforward. I think I will show it after the calculation. So now we're going to get this graph. It is the spectral density of the Fourier frequency. We will eventually have only those lines, but not this, and this, because we didn't sweep for the transverse mode number. Yep.
I have a question. If I remember correctly, you didn't mention the mesh when you introduced the heat transform part.
Oh, I just relied to COMSOL. He does it automatically.
But for solving the mode, you're actually meshing only the very limited area over there, right? And then you choose the area for the heat transfer.
When I choose the area for the heat transfer, it automatically remeshes it.
Okay.
Of course, if I was not in a hurry and nervous, I should check it.
Okay.
But
you only have one mesh point to check, right? You only have one mesh point to check. That's the geometry side.
This one?
Yeah.
Yes, of course, it is only one mesh.
Yeah. So which means you never go back to do the mode field calculation again. So the mesh is with respect to the heat transfer model.
Yes. Well, mesh is the same, just the same for both of them.
Okay.
Oh, here it's 3D. Yes, remove it, please. So I have Oh, I also wanted to show you the plot while solving function, but I forgot it, sorry. There is some function, but before you run it with plot while solving, you have to make this get initial value or just pre-initialize the plot you are going to view, and then you just hit plot and go to other thermal contours or whatever, and while solving it will be updating the plot. But I didn't show it, and we can see the thermal contours. I don't like thermal contours. I will just add surface and see for some mathematical things. And for small frequency, I can see that I have some thermal distribution, but as I increase the frequency, I have only some excitation near the mode. So the temperature haven't time to go away because of the relaxation times. So now we are going to calculate the spectral density. So on the derived values, I have a lot of some things for post-processing, and I choose integration. It is surface integration. I'm going to integrate over my, well, first of all, I have to change the solution. It will be the last solution. You can check it here. It is the same solution as here with temperature. And I choose the domains. It will be my Whispering Gallery cavity with the leg. And here, for the value of integration, what happened? Was it too boring? So somebody explode. I input here some thing is thermal SD by 2p. This factor of 2pr is due to our circular axisymmetric problem, because here I have 2D, but I have 3D integrals, so I have to paste this, and here I will leave it like that, and I press evaluate. So I have this table, but it is not in the condition I want, because I want my F to go down and M go horizontally. So I go to this table under tables, and I change its form with this sweet thing. So I press field, and I want my rows to be frequency and my columns to be M. And press update, and so I get this wonderful table, and I want to plot it. I can use it by clicking, make it by clicking results, then 1D, then table graph, but I have this sugar here, so I just press it and get the graph, and then I choose logarithmic scale, and that's what I have. So by definition, this cyan line is for zero mode, and the other ones are for other azimuthal modes. And you see that, wow, they are the same. And first it was a problem, but then we have to remember that amplitude pump factor, that it is close to 1 only for the mode I calculate, and so when I add up these noises in the post-processing in MATLAB or elsewhere, these lines will go down, and I will have only this one. By the way, I can show it right there. So this is a plot column. I hit manual, and I can highlight only the one I want to see. There it is. So my noise will have the spectral density of the following form, and the others will be reduced below. And I didn't show how to calculate those integrals. Well, I will not show much, because it's after I'm using those pre-initialized things. I can show it here in variables. There they are. So I have the definitions, and this over is overlap with the pump, and this IFEC is for the frequency part. Let's see if we can plot it quickly. So I make the node global evaluation, and here I want to input something. I don't remember exactly, but I can see here all the variables. I can plot in global. So I go to definitions, variables, and search for something. Oh, here it is, overlap ratio. And I hit evaluate. Oh, sorry, I didn't choose the correct data set. Yeah, there it is. Evaluate. Now something. Again, I forgot to initialize the integration. You know, you can use integration in post-processing, but you also can make integration while solving for some conditions, termination conditions on something like that. For model coupling, well, it is as follows. I go to definitions, to component couplings, and here is my integration. It is, for post-processing, is absolutely the same as the thing I make here, but I will use it, I can use it in formulas. So I can take instantly the ratio of integrals. Here I have to specify the domain again. Here it is, and that's all. After that, I again have to refresh my solution that I want to integrate, and I will call it as a function. So here is the name of function, and I will write something in top 1 of my field. I'll show it right away. It should be here. No, not here. Here. And so you can see that those things are actually yellow because he doesn't know. He just highlights this. He now doesn't know the variable of q, and here he there is not very good. But this is yellow because he doesn't know this integration operator. And here how it is applied. So int op from my field. Yeah, it's actually this like it is here, but inside the int op. And then I can use global evaluation to plot it, and you will obtain the following picture. So that is for overlap. You can see that all the modes are 10 times less than the main mode, and for frequency part you can see that the modes, the spherical modes with m plus p equal some constant, they're high, but all the others are small. And so for thermorefractive noise, we don't need to calculate all the modes, just the one. But maybe it is a good practice to check it every time. It's not very complicated. So I will not calculate this model. You can download the base of the model and go through those steps by yourself and calculate it in the exercise section. I will go to Brownian noise. It is a bit more interesting and complex and not well defined, but nevertheless. For Brownian noise, we have boundary displacement, and we can, well, it actually was some days ago. You can rewrite it, and if you want to take into account the different polarization, your form factor will be something like that. It was when we discussed the optomechanics, yes. And you can see that naturally we get here the surface integration because of this gradient acting on the volume integration, we actually get the surface integration. And here U is the displacement field, apparently. And as you can see, our generalized coordinate is displacement field, and our generalized force is boundary force, because it's boundary integration. And our master equation is solid mechanics, just as it was before. Here is the main equation, and here is the boundary condition. And here this A to A ratio is also important because here we are waiting for the resonances. And those resonances will be much higher than those 10-time attenuation. So the difference for Brownian noise on all mechanical ones from the thermal noise is that here we actually have to calculate all the modes. Not all the modes, but at least azimuthal modes, because we will have those azimuthal mode resonances in mechanical system. For that, and of course the losses are very important, but here I just use the formalism of the loss angle. So I think that I already know the Q and calculate the losses just as the full energy times the loss angle. Here again have the summary of the what I have to do, but you can download the model that is actually calculated for Whispering Gallery modes. Here it is. It is the toroid, because it's more beautiful for mechanical modes. Here it is. I also inputted the parameters and Whispering Gallery mode variables and got the guess for the mode and for its dimensions, and cut the region and calculated. So here is my mode. I can look for some other modes. This is TM mode, and this is the second vertical mode. Should be. Come on, yes, here it is. And here I also have already calculated the ratio for frequency and for the overlap. One thing I should mention is that the calculation of overlap is not very good, because you have to mesh this domain better. Because when I calculate this integral overlap, I assume that I have some Gaussian here, and I need to know the field here precisely. And what is this? Oh, here I have this logarithmic field. To plot it, I just use the cut line, as you remember how to do that. And this cut line goes from here to here. And I plot the logarithm. I plot the field in logarithmic scale, and I see that exactly those fifth mode is not very good. Is not very good calculated. So because I have my pump somewhere here, and I have this numerical noise, so I do not believe to this point. And well, the electromagnetic part is ready, so I'm going to add the structural mechanics model. By the way, how much time do I still have? Is there any time left? No, it is not Switzerland time. So it is 12 o'clock. So I have about 15 minutes. Okay. So briefly, now I have actually, at the last version, the azimuthal, the solid mechanics obtained this circumferential mode extension for axisymmetric with the azimuthal number m. But for my calculation, it is not very useful because actually it does it only in frequency domain and eigenmode domain. So I will not be able to solve stationary and sweep for frequency. I'm afraid I will not have time to say why it is important, but nevertheless, I have to, and before this summer, I had to make my solid mechanics to really deal with axisymmetric problem, because in RAW, it even doesn't know about the axial displacements. That was a shame, really. And so to change the equations, I go to this equation view section. Here I also have my selection union to instantly highlight my cavity. And now in equation view, I will see all the variables and equations that are preset in COMSOL. And according to the notes I made, I have to find the variable ERphi. It is the strain tensor, and change it from 0 to this. So I just add those derivatives over the phi angle with respect that I have an exponential complex exponent over phi. So here it is again, it is Im over r. So I can sort it and look for solid E, A, B, C, D, E. Where is it? C, D, E. Why that's so. Oh, E, yes, E. Somehow I can't find it. That happens. Maybe I should change the study. Yeah, it was some. Yes, here it is. What it was? It was R-phi. So R-phi. It was 0, and now it is non-zero and complex. And COMSOL will highlight it, that you changed the equations. And I think I will not try to do all of this. You can do it by yourself. Next, I will have to tweak the expression for my master equation. I have to, because before this summer, COMSOL thought that all the fields are real, and if I introduce here these derivatives, it becomes complex. So I have to add this complex conjugation to for the equation to be correct. Yes. So I also change it in equation view, and so on. Then I add frequency domain, just as I did for thermal problem, and then I have to add another coordinate, because, as I said, in RAW till last summer, COMSOL thought that you never get non-zero axial displacements. So I again add the weak contribution, and here on the weak contribution I can add auxiliary dependent variable. So I will have another variable, dependent variable, which COMSOL will solve for. I name it V. Just to maintain the logic, he calls the displacement field UV and something, and WV is. But however, I also have to change this definition here, because this V will always be 0. It is that awful 0 that COMSOL have, so I rename it to V old, and I will not bother it with it further and forget about it. Then I also have to tweak a bit fixed constraint, because now it is written only for those variables that COMSOL have inside, but it doesn't know about my new auxiliary variable V. So I have to add additional point-wise constraint here. No, come on. What it was boundary number 2. I can add it just like that. Here it is. And I plot here V, so this V will be constant on this, will be fixed as I need. And you can see that now you have this brown dot. It means that these two boundary conditions are contributing to each other. If you had here a red triangle, it will mean that the below one will substitute the above one. But it's not the case here, but it can be the case. Well, for example, for this, the fixed constraint is substituting the free constraint. Well, what next? Yes, then I add my boundary load and sweep over M and F like it was in previous ones. Probably I will not do that. I wonder if I can show you the final model. Probably it's not there. No, there are only two of them. So after you calculate that, you will get those modes, and after you do the post-processing, you will get something like that. So while sweeping the M number, when M number is 0, I have only one pike that corresponds to the mode I'm interested in. For M number 1, I will get one of, I don't remember which, but one of those peak pikes, and the mechanical mode profile will be like that. And for the next one, I will get another pike, and the mode profile will be like that. So it's second mode. And then I have to use some MATLAB or something like that to add up all those things with respect to the amplitude coefficients I get before. I'm afraid I'm out of time, so if anything is unclear, please ask questions.
Showing of the data is kind of a difficult thing in COMSOL. Is it like a common thing to do to export the results in MATLAB directly? Manipulate everything in MATLAB, doing the integration and stuff?
Well, I usually try to separate things, so I get some table, then I add it to table export, and get here file name and doesn't include the header, and it just gives me the table just text, and then I import it to the MATLAB. It has just one word function to get the data from the text file, so it is quite easy. It's straightforward.
But in producing these tables, I mean, so for instance, I could not understand everything you did. Like, it's a lot of manipulations just to produce one table. Wouldn't it be like a lot more convenient? Because I mean, usually in your brain as a physicist, you know exactly what you want to do, and then you need to comply with the interface here, which is super complete, certainly, very complicated in some sense, as compared to anything where you type functions. Because I mean, when you want to integrate a certain quantity, you know what this quantity is. You extract it from the physical parameters that were simulated. So it's not something that is commonly done. I mean, you don't do it.
Well, if you want, you can use that MATLAB interface for COMSOL that was the first speaker speaking about. It is just an interface, so you can just control your COMSOL from MATLAB. But from my point of view, it is a bit more complicated because, well, it depends on you. If you like to hard code things and not using GUI, but just using the command line, it will suit for you. But it's not answer. Well, to export the data, there is the export node. You can export the data, you can export plots, mesh, tables, and whatever you like. And then you can feed it to MATLAB. It is, and manipulate as you want, as you wish. So there are always different ways to do things. So, yeah. Yes, exactly.
So all the solutions that
COMSOL
handles, they're in the weak form?
Yes, precisely. So if you study this weak form formalism, it will be quite easy for you to tweak the equations just in equation view. Well, if you need some more complex things and not related to some existing interface, you also can write your own interface, or you can just use the mathematical mathematical interface, which advise you, again, 3 different ways to input equations. It's a general form, it's coefficient form, and weak form. And there are plenty of capabilities. What else? I think I can find the model that was already calculated and show it to you somewhere inside my server. Let's try this. What is the last thing I want to speak? That there are more noises. For example, a thermoelastic noise that is connected to thermal expansion. But the algorithm is precisely the same. You know this relation, and you actually understand that the observable is like in Brownian noise. Yes, the observable, because it is also the boundary displacement. Then there is a bit trick, because the generalized coordinate is displacement field, not thermal field. However, we are going to calculate the thermoelastic noise. And the generalized force is boundary force. But the master equations are both heat transfer and solid mechanics. So you combine all those things I did before with a minor change. So now we have the thermal pump, which is thermoelastic damping. Because the idea is to calculate thermal losses. I calculate thermal noises, then the losses are thermal. I calculate the Brownian noises, then the losses are Brownian, mechanical. So here I again use these equations for my mechanical part. Then the mechanical part is fed to the temperature part, and then I calculate the temperature losses. Oh, that's a pity. Well, basically, I can finish now and wait for more questions. Well, the server I'm doing the calculations decided that that's enough.